and welcome to another book talk by the Gruyter. My name is Christene Smith, and I'm an acquisitions editor in material science and industrial chemistry. Today, we're going to be learning about nanochemistry, focusing on our new book on the topic, From Theory to Application for In-Depth Understanding of Nanomaterials. I'll be joined shortly by the editors, Xuan Grace Wang, Sajid Bashir, and Jingbo Louise Liu, who all are professors at Texas A&M University in the United States. Today's topic will be a broad overview touching on the sections of the book, but for a more introductory level, so any academic can tune in and learn more about nanochemistry. In the book, which is a graduate level textbook from us, you can expect to understand what is nanoscience, what does it mean? Obviously, it means nano, so very small things, but a bit more on that. How can we make nanomaterials? Characterize them, which we won't get in too much into today, but you can check it out in the book. And what applications can they be used for? We'll be covering this all today. And I hope you enjoy this book talk and stay tuned for the rest. So now, the question on everyone's mind, nanochemistry. What is it? I think a lot of the people who are watching this video might hear nano and think of some sci-fi things or other applications, but they don't really know what it means. This is where we're going to start our chat today. What is nanoscience and nanochemistry? And why don't we start with Louise? Maybe you want to give your thoughts on this, and then we'll spread it to the other speakers as well.
Yes, I think nanochemistry is a discipline of chemistry. And if something is small, let me ask everybody looking at your hair. So the diameter of the human hair is 60 to 120 micrometer. It's about 10,000 or 100,000 times bigger than the little nanomaterials. So nanomaterials have lots of special properties, so you can tune the structure, the morphology to achieve your final goal. So that's my understanding. Just something small, something unique, and you can control it to have multiple applications for these materials. Yeah, thank you.
I like the example of looking to the hair, because I think it's hard sometimes when we hear the word nano to even think on what scale does that mean. Next, why don't we go to Grace? What does nanoscience and nanochemistry mean to you?
For me, nano, that is a prefix. If you take general chemistry, and your teacher will definitely tell you, nano means 10 to the negative 9. So that is related to the size. So you can imagine any of the nanomaterial will be between 1 to 100 nanometer. Okay. And what nanochemistry means to me is, based on my experience, I have been focused on the sizes. So the size coming with two different physical properties for me. It's going to be porous or non-porous. You can consider that like a big giant building. The porous nanoparticles are each of the rooms. You can place many things in the room. You can have people, you can have chairs. So it depends on the host, the type of the host. You can put a different guest inside of that. So that leads to the different application. That's what I'm most interested in. Yeah.
Nice. Another good analogy, but it's a different one, talking about, it's not just that something's really small, but it can have holes, which are nano size, and what can we put in them? So I think that was really great as well. And last, let's go to Sajid. What does nanoscience and nanochemistry mean to you?
Well, I think Grace has mentioned, you talk to a physicist, they'll say nano is a literal description of size. But I think nano is also coming into our everyday vocabulary. We have nanopod, nano this, nano that. And so for us, nano means very, very small. And the reason why people are so interested in nanochemistry, nanoscience, is that if you just imagine atoms as people, if you have two layers of people standing, the way they behave is very different. And so if you have, let's say, bleachers, and you got people standing on the first row and the second row, and you're in the middle of the field, a lot of times you will not see the people in the second row because the first row is blocking your view. If you only have 4 people standing, right, and you're in the center of the pitch, you'll see all 4 of them. Now, what that means in chemistry is that when you have nanomaterials, because there's so few atoms, those atoms actually behave very differently than if you had a billion atoms. Because in a billion atoms, most of the atoms are obscured from our viewpoint. They're in the center of the solid. If you have a cube, they're in the center of the cube, whatever. And on just the corners, you only have a few atoms. But if you only have 20 atoms, then majority of those atoms, will do something because they're not hidden, they're not obscured. So I think that's the advantage in nanochemistry, nanophysics, nanomaterials, is that they behave very, very differently than their bulk counterparts. And remember, our toolbox in chemistry is only roughly like 111 elements, right? And of the 111 elements, pretty much the only ones we can buy in bulk are these transition metals in the main block. And so our toolbox is very limited, but this allows us to reutilize those tools in a really different way, a really exciting way.
Yeah, totally. I think also when you're in a general organic chemistry class or inorganic chemistry class, everything's on bulk scale. You put everything into a reaction and just everything happens all in one phase. But when we get to nano, everything is so much more focused on the surface, what's happening in that surface level. And so, yeah, I think you explained that really well. Okay, so now let's go to the next question, which is, how do we make nanomaterials? Okay, so we have an idea what they are. They're small. They may have pores. They may not. We're looking at a lot of surface science. But how do you make them? How do you make the building? How do you make the hair? How do you see those 4 people on the football field? So let's switch up the order a bit. And why don't we go to Louise first?
Oh, with me first, right? Yeah, because I have been teaching nanochemistry. So we're teaching students to synthesize materials using 2 approaches. One we call this bottom up from small to big. Another one is top down from big to small. So in our book chapters, if you take a look, we have all these different synthesis methods. So in my lab, we are doing lots of, we call the feasible and easygoing, cost-effective methods. We call the sol-gel methods, micro-emulsion methods. And we also developed something called plasma-assisted chemical vapor deposition. Just you make something to be vaporizing. So, and then they are going to be re-deposited onto some substrate, such as we can produce different aligned carbon nanotubes. They are aligned very well. So like trees aligned. And then we do a little spraying of the platinum nanoparticles to produce lots of useful electrochemical catalysts. This is one example. The second example is from big to small. So we're using one method we call the ball milling. Just imagine you want to make your garlic smaller. So you punch it and you start grounded. It's something similar to this major principle. So grounded from big particles into smaller ones. Definitely, we control different variables, optimize these synthesis parameters to achieve the materials we designed. Yeah, I will leave some spaces for the other 2 editors.
Absolutely. This time, why don't we go to Sajid next? When you think on how to make nanomaterials, what comes to your mind?
Okay. Just to clarify, we did not invent plasma-assisted methods. We adopted them. I think of the 3, Louise and Grace are the practitioners. So if they were medical doctors, they're the ones who will be with the patients. I'm more in the back office doing the billing and telling them they didn't pay. But in principle, we can do them from bottom up, which is basically take a brick and cement and just make the wall the height you want, one brick at a time. And typically the way that would work is stoichiometrically, you take your metal salts, whatever you want to make, and your ligands, and then you do the synthesis in that way, in a controlled way. The other way is mechanically ball milling or whatever mechanical method you have. You could do laser desorption and desorb those atoms off. And that would be, my wall is too tall, too high. And then you just take the gravel and take one brick off, one layer off at a time. There's two ways. But the people that I'm interested who listen to are in Louise and Grace, because they're the ones that are in the lab and they're the ones who actually make these beautiful molecules.
May I echo something? I'm the one get the hands dirty. Sajid is a smart one who designed it and gave instructions.
Architect, amazing. Yeah. But I think with that good segue, maybe now we go to Grace to hear more about the nitty-gritty of lab work and how you make some nanomaterials. So go ahead, Grace.
For me, I'm more familiar with those bottom-up approach where we're going to use something called the solvent thermal and hydrothermal. So solvent and the hydro are indicating the type of the liquid part we're going to put. We call it solvent, right? And solvent, most of the time, it's going to be organic. So anything you smell like daily inside of the paint, it's a majority of the organic. And hydro is another prefix for water. So you can imagine the hydrothermal will be a little bit cleaner or greener than solvent thermal. And like building houses or building Legos, so you design the type of the framework you want to. If you live in Canada with a lot of snow, then I guarantee you your roof will be rigid. So that way that the snow will not destroy your houses. So that's the way you design. But if you are in South Texas, it's a little bit more flatter for the roof. So you're going to change your structure of the ligands, the framework. And the reason why we introduce those solvent is trying to occupy the space. So it's like I have building a couple of the bubbles. Imagine your solvent like a bubbles. Put the bubble together and then there's a gap. And then that gap will be filled with your organic part. And then you can use your metal pieces to use as a connector, the concrete, to glue everything together. So from there, you do have your framework, entire structure. And then after the reaction, you can remove those bubbles. Just one pinch, the solvent is going away. Those are the synthesis method I'm familiar with.
Yeah, so a lot of analogy on building with bricks and Legos, making our framework. And I think it's also really important, you say that you kind of flood the space and remove the solvent. This sometimes it's harder to understand, but when you think in this way, it begins to piece together, let's say.
And
okay, so let's go ahead.
Just one thing I'll add about the book. Grace has mentioned a really good example. What may not be obvious from listening to Grace is that the method she spoke about, which is called metal organic framework, that's a specialty method. So that's, if she's a doctor, she would be like a brain surgeon. That's a very specialty. Not everybody does it. You have to be very good at it. So in our book, we actually go through each of these synthesis methodologies that Louise mentioned, top down, bottom up, and then we go deeper and say, okay, for top down, there's 5 ways. 3 of the ways that worked in our hands are these 3, and we describe them in detail. Bottom up, right, there's 5 ways. And then we talk about MOFs, specifically MOFs. Grace talks about MOFs, all the different type of MOFs, how you can make them. And one thing the audience, beginners will have problems is, what atoms do I choose? What metal? Because metal organic framework is metal and then organic. What metal? Grace mentioned about the organic, right? They're like triangles, they're like squares, they're like pentagons. Well, if the triangles or pentagons, the angles will be different, a little bit different. One's like that one. And so you want bigger spaces, small space. Okay, but the metal is also really, really important. And so in our book, I think that's the nice thing about somebody who's not an expert like Grace or Louise, is they read the book, and that experience, that knowledge is given to them. We don't say this is what we do. We say this is what we do and this is why we do it. And I think for the beginner, it's important because, why are you doing this, right? A lot of books don't mention that. They say, okay, you want to make a table, right? Make a hole in the leg, make a hole in and then use a wooden dowel. But why would we make a hole in the leg? Why would we make a hole in there? Why are we using wooden? That's never explained. They just say, here's how to make a table. So that's one big difference between our book and other books you may see is we explain to you what to do and how to do it, but also important why to do it. Because once you know the why, you could design your own molecules. You don't have to copy our molecules.
Yeah, it's more than just a recipe.
Yes, exactly.
The whole package kind of.
Right. Yeah, the thinking behind them. Yeah, exactly.
Yeah, totally. So now we're just going to go to the last question. Sadly, the last, although this has been a fun conversation. So it's, what are some uses for nanomaterials? So we know what they are, how to make them, how to characterize them. But I think the big question is, okay, so what? What can you do with them, or what are they useful for? So for this, why don't we go to Louise for the beginning?
Okay, I will give a bigger picture, I think. So for me personally, I believe the nanomaterials definitely have multiple applications. Like Dr. Fleming mentioned, there are plenty places for us to explore the small worlds. For us, especially for Sajid and myself, there are two major directions. One is applied in the sustainable energy field. Another one, I will say biomedical related. For sustainable energy related, such as battery. So recently we did I call it a new electrolyte, halide-based electrolyte, which is a solid. And I found the ionic conductivity is very similar to the liquid ones used for battery, solar energy, and supercapacitor, also fuel cells. Another energy-related application is the electrolysis cell. Our collaborators and us, we figured out how to produce ammonia, NH3, through the electrochemical electrolysis method. As such as our hydrogen production, I call it is a green hydrogen production using electrolysis to break down dirty water bodies into hydrogen and oxygen. The second bigger direction, we developed different disinfectants. So it spray it to kill the bacteria, such as gram-negative, gram-positive. Unfortunately, our materials essentially kill the good and bad living organism. So we don't know how to differentiate it. Maybe Sajid knew some ideas. And also in collaboration with other faculty members from a pharmacy school, we tried cancer seronostic diagnosis and therapy. Some other projects is related to the human health, such as you want to see the physical fitness. So Sajid and me, we did the creatine sensing, and also we working on the human eye cell, the RPE evaluations that related to toxicity study. Some other ones I think I want to mention in collaboration with the local law enforcement center, we developed some fingerprint development agents, try to help the local officers to study or to develop the fingerprints more accurately and more individually, specified, customized. Another goal is try to see if the little baby, they get abused or not. So we use something we call the biologically compatible metal organic framework-based nanoparticles, has the better distinction. Yeah. So I will leave it for both of them to explain more. Thank you.
I think one thing's clear, you mentioned so many different avenues that you can take. it's not just only useful in sustainable energy or only useful in biomedical. For something so small, the use is so huge, and I think that's one really cool thing that I find about nanomaterials. But since you mentioned a lot of Sajid's projects in yours, I think we'll hand it over to him next, and then we'll finish with Grace. So Sajid, why don't you take over?
Okay, so I went to Aberdeen Medical School, and that medical school actually used to be a monastery. And so when those monks were threatened by the king, they said, "Oh, okay, we'll give this monastery to the university." And so there's a little story about when the Lutheran monks would graduate, they would ask the cardinal, Christianity, how do I do good? And they were all the cardinal always said, "How long is a piece of string?" And they would meditate on that, and they say, "I don't know." And he say, "Well, exactly. There's no fixed answer. You just do good. There's no recipe for that." And so for nanomaterials, there really is no real answer, because it's like saying, "How long is a piece of string?" Because nanomaterials, because they are very small, there's few atoms, they behave very differently. And so we go on and we say, what area of chemistry, physics, engineering we like to do, but we can't with traditional materials. And we then, everybody focuses nanomaterials on those. So Louise mentioned some of those examples, right? Batteries today can store more energy than the batteries from the 50s, because they are now engineered with same atoms. I mean, we still have lithium, we still have sodium, all right, but they're nanomaterials. Okay, and so in the last 5 years, people have gone into areas where traditional materials can do good, but because nano can behave differently, they can do better. And so now you can go to your supermarket and buy, potato chips that have nano coatings on the envelopes, keep them fresh. Socks with nano silver in the front, right, to keep your feet not from selling. And so literally any application that you believe that you can do chemistry that is really hard to do with traditional materials, or do chemistry better, we can do that. And so one example of nano that we mentioned, maybe the audience is not familiar with, is called therognostics. Thero is the short for therapy, and gnostics is short for diagnostics. In the past, you would do an MRI, and then you would get an injection, or some treatment. Nanomaterials, because you could like Grace does, you could connect two different atoms, and so you have two atoms, right? And the first atom is really good at giving light when it hits a particular cell, and the other atom is really good at killing that cell, right? So now you basically put the injector in, and the cancer cell, the first atom hits the cancer cell and glows, and we see where the glow is. And the other atom, it's a barbell rotates and kills that cancer cell. So we can do thero and diagnostics in one package, and that's not possible with traditional chemotherapy, right? Chemotherapy is a bullet. You tell me where to shoot. And I think that's the advantage of nano. So as time goes on, you'll definitely find more and more and more applications of nano in any field you could think of. Louise mentioned environmental science, energy science, biomedical science, right? And I think those sciences are really important, but it'll be also in mundane stuff, right? Jackets that change color, keep us cool, socks that keep us, our feet dry, and So I think wherever the imagination is, you're gonna have nano in the future.
Yeah, somehow they're more sophisticated. You can do more things than you could do with the bulk. And
yes, yes, absolutely. And if you fly a lot, I don't know if you fly. I think you do fly. If you take the Boeing 777, a lot of those materials right now, composite materials, nanomaterials, they have nano coatings in the glass. I don't know if you noticed the windows, they have nano coating. So those glass, they'll dim down themselves. You don't need to take a mechanical
shoot. Yeah, I have seen those. Yeah.
Okay, those batteries are nano, right? The flight sims, all this. So we're going from traditional engineering to new engineering with this nano, because these atoms, they can behave differently. Now they could do, they're lighter, they conduct faster. Those dots are closer together, so your pixel density is higher. That means the color intensity is higher, the resolution is higher, they're faster. They could do 2 things, 3 things, 4 things maybe. And so I think as time goes on, your kids, my kids, we're going to see more and more nano applications out there because they replace traditional materials and because they are lighter and they do the same thing a lot faster.
Absolutely. Okay, on that note, I'm going to hand it over to Grace to finish it off about some last final uses for nanomaterials. Although I shouldn't say final, because as Sajid just said, there is no final in this area. But yeah, maybe some of your favorite or more exciting applications that you can think of.
There's one thing I will say. If you ever wear makeup, you probably are wearing nanoparticles. Yeah, a good example is in the summer, everyone trying to put on some kind of sunscreen, right? The major component is the titanium oxide nanoparticle. The different prices you got from your makeup is priced for nanoparticles. That's one of the major things. And another thing is for companies recently, they have been raising their awareness for social environmental responsibilities. So like Louise mentioned that your sustainable energy resources are a big part in the nano applications. So you probably can hear that there will be some porous nanoparticle are using as a carrier for different applications, such as they trying to store hydrogen, they trying to store natural gas. So there has been experiment from the chemical company BASF. They have partnered with the scientists and then trying to drive a vehicle that is powered by nanomaterial moth captured natural gas to reduce the cheaper. Yes. So I know you like that one. I do too. That's exciting. And another thing, we keep caring about the environment. So there's so much carbon dioxide we capture. That's why we are also using those porous nanoparticles to capture carbon dioxide. And that is a great use for me, I feel like, is everyone need to care about the environment. Those are the applications I'm excited about. And then another one I will say in our book, we have a specific chapter mentioning about water harvesting. And so we build up the devices with nanomaterial inside and then trying to collect water from in the desert. And this will allow us to live in many places we never lived before. Nanomaterial really opened the door for many, many uses. And like what you said, we are right on the road. There's no end for that.
Awesome. I think that's a great way to sum up the future of nanomaterials and what we can expect. And yeah, I want to thank you so much for taking the time to sit down with me and have this chat and talk about your book. Want to give one final shout out. So the book is Nanochemistry, From Theory to Application for In-Depth Understanding of Nanomaterials. You can get it already now on Gruyter.com. There'll be a link in the show notes. And with that, I want to say goodbye. So see you all later.